Okay, so in this next video we're going to work on simply importing our netlist from the previous week. So this is the same circuit that we worked on last week with all the footprints attached. So let me go ahead and select all the components and remind us where we were at here. So I selected all the components and then went to Edit Properties, but now I'm going to go to Parts. And remember, we had this PCB footprint, and we entered all these custom footprints that we had created. Now, I know there have been some people that have had some trouble with Aporto not letting them change the path names. So, if that's the case, I'm going to write off into the text here some things you can use instead that are built-in footprints. So if you haven't been able to get Aporto to accept, you changing the path names, then you can try this here. So what we're going to do here is for the LM741, you will use the footprint dip8_3. I meant to actually hit Control Enter on that for a new line. So that's the footprint name you'd use, is dip8_3. Now for the headers, J1, J2, those footprints would actually just be jumper4. Then for my resistors, the footprint for them would be, now this is a little bit longer here, AX, which stands for axial. 375, that's actually in mils. 375 mils long is what we're saying the resistor is. And then I honestly don't know what this second number is, which again is kind of something I don't like about the naming convention that is used by Cadence, because some of these numbers I'm like, I don't even know what that 100031 is, or this dip8_3. Why is there an _3 there? I mean, I don't know what the reasoning is behind these. So that's why I don't like to use them. But if you're in a case where you're not able to get Aporto to accept the change in path names, we can go ahead and use these. And then the last one is we need one for the capacitors, and that would be CP CYL for capacitor cylindrical, the number 1 D250 LS 1031. So the same kind of 100031 attached at the end here. So those would be the footprint names that you would use if you're unable to get those custom ones that I had uploaded and unable to get the path names set correctly. So this would let you still continue on with this example to do the layout, which again, just like we did last week where I had you recreate this circuit as part of your homework, I'm going to be having you complete this circuit as far as doing a layout. So again, I know I'm emphasizing it over and over again, but if you can't get those, if you don't have the ability to adjust those path names, then you need to use these footprints instead for the components. All right, well then we're ready to actually launch the PCB editor, and I already had it launched here. Actually, this component here that I was working on actually is an old one here, and it actually has pins that are in the wrong orientation here. This is supposed to be like an SOIC chip where these pins here should be rotated 90 degrees. Now, what's kind of interesting here is I'm going around and selecting them is that you don't have to like exit this program to make a modification. You can actually just select one of those pins and do modify design pad stack, and then okay, I'm going to select this one, I'm going to say edit, and then it brings up the pad stack editor right there, and you can see I have my width and height in the wrong order there, and I could edit all of that stuff, get it all changed, everything like that, and I'd be all good to go. Now, whoops, I'm not going to care about doing that because that's not the purpose of this video. But it's just a little interesting thing that you can do there. Another thing you could do is you could do select and then do replace and say, okay, I want to replace that pad stack, and then I could, for instance, replace it with one of my newer pad stacks. Let's see, RSR, like with this rectangle, for instance. And then I could just say replace, and then it replaces all those pad stacks. So another kind of interesting thing you can do there as well. So, but again, that's not what we're focused on here. So I'm going to go to File, New. I don't want to save anything to that. Now, in this case, we're not doing a package symbol, we're actually doing a board. So I'm going to scroll up here. There's board and board wizard. We're going to use the board wizard predominantly. The board is definitely for more custom types of boards if you have specific kinds of shapes that you need the board to be in, or just it lets you set up all of the design constraints manually as opposed to somewhat automatic here. But we're going to go ahead and use the board wizard. I'm going to browse here. Now, you have a lot of options on where to browse to save this. What I like to do, and actually I need to go back to the circuit simulator because I don't remember where I saved this. Layout, I wonder. Okay, so it's in my OneDrive account. So I'm going to, in my OneDrive account, I'm going to go to Cadence, ECE 1000. I think it is, yeah, it's this one right here. And then this layout 1, I believe is the one here. Okay, it says poor directory management for me. Let me make sure that I've got the, yeah, layout 1. And now I'm in here, and I have two options. I could save it right here. And actually, you don't even have to save it in any of these directories. You can save the board file wherever you want, but I'll show you why it's sometimes good to save it in a particular location. I'm actually going to save it inside this Allegro directory, because that's what this program is. This is Allegro. So I'm going to save it in the Allegro directory. And I'm going to say this is layout, and I'm going to go ahead and do 10/15/2021 because that's when I'm doing this video. And so I'm going to do the board wizard, and I just crashed the program, which if you've been using the ones in the lab, that may have happened to you before. It's always fun. It's probably because I was tabbing back and forth between the two things too much. So File, New, Board Wizard. I think it's already in the correct directory now. No, it's not. So Cadence, ECE 1000, Layout 1, Allegro, and then we're going to call this, I can just open, but then I'll call this Layout 10/15/2021, and then I'll click on OK. Now, don't know why the board wizard opened down there. It's probably because the last time I used this. Now, it's going to basically kind of say, hey, this is what's going to help us do. So we're just going to hit the next one. Now, there's a bunch of templates and other things, options here that we're going to say that we could import. If you were working for a company, you might have these templates or something. We aren't going to have a template for this. We're not going to have a text file or a parameter file. Parameter file would be maybe being able to set all the constraints and everything else like that. Board symbols are used to import board outline and other related information. Do I have this? No, I'm not going to import that. So that's if we were importing data. Now, again, select the unit here. I'm going to select millimeters because that's what I've been in. Um, select the drawing size for the board. I think that's just for if you're wanting to print it out. So like for instance, A1, I'm going to just select it as A4 for printing it out. If you're like wanting to print the board out once it's done. This you could set at A1. It doesn't really do anything harmful as far as the layout, but I'm just going to go ahead and set it to A4. Okay, now here's where we start having to make some decisions here. How much do we want to have our grid spacing? So those are those little dots there, and one of the things you have an option to is called snap to grid. So if you're placing components, you can snap it to the grid points. And so right now the grid is set so it's going to be every 1 millimeter there's going to be a grid point. And I think that's okay. I mean, you could make that smaller. I mean, the issue, you make it really small, then it's too much going on as far as like you're not really snapping to any grid at that point. You may as well just have no grid spacing. Now, etch layer count. Uh, this particular board is only going to have one layer. I often just leave it at two. You can do more layers, but currently two is what we would be able to do in our current lab facility, and that would mean that you have a top layer and a bottom layer. And so I'm going to leave it at two just so that we can go through and see what we have to be careful with when we're doing the routing. And then we always want to go ahead and generate default artwork films. And then it asks, what are these different layers? Like, are they power layer, power plane, routing layer, or power plane? Well, for us, these are going to be routing layers. A power plane, again, is for like a ground plane, or literally like, hey, there's 12 volts on this. And again, for complicated designs, they typically have not just like, routing layers, but they also have layers which are just complete like ground or power, because it actually makes it easier to connect power and ground up to the chips. Okay, so now we have minimum line width here. So this is actually talking about what's the minimum trace width for our traces. And so what we want to do here is we want to kind of think through this here. And this is actually where I've often used mils instead of um, millimeters. So I'm going to go ahead and enter in what I normally do for mils. So I normally do 40 mils um, because that's a nice thick trace in the sense that it's you know easy to solder on, things like that. Now, as far as really what the trace width should be, that's 100% dependent upon the type of signal that's going through that trace, and how much current is going to be going through there, because depending on how much current is going through the trace, you have to have a certain thickness for it. So this is kind of arbitrary. There are actual standards as far as how thick the trace needs to be for current. Actually, let's see if we can just see if we could do this here. Width of trace for current. And there's even a table here. So let's just see here. Okay, so current, um, which says it's in amps there, which I don't know if that's correct. I'd have to double check that. That doesn't seem quite correct. And here, this graph is actually pretty good. Maybe it is in amps, but basically current capacity if you have 1 ounce copper, which is what we have, which basically is talking about the actual like bottom of the copper to the top of the copper, which means like the actual thickness of the copper film is 35 micrometers. And so, it's getting here the trace width, so like a trace width of 1 millimeters is going to be able to hold plenty of current for us. Um, and it also goes into more information as far as, how you can determine the um, max current, but it also varies based off of temperature as well, as far as what you can have as far as your max current. So, but as I said, for us, we're just going to do a relatively standard, and so it's 1 millimeter. Now, if I just do that, it's going to automatically fill in these line-to-line spaces, line-to-pad spacing, and pad-to-pad spacing. And these are design rules. And what that's saying is that when you have 1 millimeter for line-to-line spacing, here, let me draw out what these are saying. That will probably be easier than me trying to just describe it here. Um, so let's go here. Okay, so the line-to-line spacing is, okay, I have a trace here. And now I've said that the minimum width of this, it's not saying the widths have to be, but I'm saying the minimum width is 1 millimeter. So what we're saying is this trace here, if I was looking at the dimension here, that has to be at least 1 millimeter. It could be bigger than 1 millimeter, but it has to be at least 1 millimeter. And then to say the line to line spacing would be, oh, I've got another trace here, and this distance here, that is my line to line spacing. So it's saying that, well, if you have a 1 millimeter trace as your minimum width, it's by default setting it to be 1 millimeter line spacing. Now again, there's probably some IPC standard for that. I don't know what that is. I'd have to look it up. But I sometimes set this to be a little bit lower just so that I can move traces a little bit closer and everything. So I'm going to just set that at 0.5 millimeters. And then we also have minimum line to pad spacing. And so minimum line to pad spacing would be, and this is important because, for instance, let's say we have like a dip package here. Now this is not something you really want to do, what I'm going to demonstrate here, but it demonstrates what the line to pad spacing is referring to. So let's suppose I have a trace connected up here, and I want to connect it over to this pad here. There's lots of ways I could go and do that, but suppose I wanted to try and go like this way to connect it up. Now that's not necessarily the way I'd want to do that, but let's suppose I did. Then this distance right here, as you might guess, that is the line to pad spacing. And so we're saying that has to be at least 1 millimeter. And again, I sometimes go ahead and just set that. I'm sure, again, there's an IPC standard, but I set that a little bit lower. And then pad to pad spacing, you can probably guess, I have it right here that we could show here. The pad to pad spacing, this is pad to pad spacing. And again, I kind of put this down to 0.5. And now, even though this is going to be what is called a single-sided board, we're only going to have traces on one side of the board, you always have to have a default via pad stack. And there's a default one in the library that I always just use because this always has to be filled out, regardless of whether you're going to use vias or not. And so I just type in via, VIA. There's a pad stack called via, and so I just use that unless I'm going to specifically use one that I want to use because I am going to be using vias. Now this is another interesting thing. It always wants to do a circular board for some reason, but we often do rectangular boards. And then, the height and width of this board. So let's make this board And this is where remembering that I actually often do these in um, mils. Let's make this board 500 mils, so that's 12.7. So we'll just say 13 by 13. That means it's roughly a half an inch by a half an inch. Now, this corner cutoff is showing this little dimension here. And sometimes you want that corner cutoff because of case like brackets. Like in order to fit the board inside a case, there might be screws that are going there, not mounting holes or screws, but this would be like screws or something to actually close the case so that you don't see the circuit board anymore. Like just how like there's a circuit board inside your cell phone, but you don't actually see it because there's a case over it. Okay, we're not going to do corner cutoff. Route keep-in distance, what that's referring to is how much distance we should keep trace from the edge of the board. And there is an IPC standard for that. I can't remember what it is. So I'm going to say I want to keep that for this point at 0.5 millimeters in from the board. And then there's also a package keep-in distance from the edge of the board. And so I'm going to go ahead and set this at 1 millimeter. And that one is a little misleading because sometimes you have to be careful with the pack and keep it distance, because sometimes packages you want to put them up against the edge of the board. Like if you're talking about connectors, like if you're talking about making a power supply, well, you're going to have a USB connector there, and you're going to want to have that pretty close to the edge of the board or at the edge of the board, because you need to have that so that somebody can plug in a USB cable. So know that just because that's here, it doesn't mean it has to be a number. You can have it be 0. Same thing with the route keep-in distance. But I'm putting them there as non-zero so we can see what they do. And then it's going to come up with this board and say, okay, here's my board. So I'm going to go ahead and hit finish. And now it's pretty small here because it's only half an inch by a half an inch, which actually I might have to make a bigger one now that I think about it. But we'll see if this one works for us. And what we can see here is this gray outline is the actual outline of the board. This oranges is the route keep-in, and then this purple is the package keep-in distance. Okay, now before we actually go and do anything else, we got this board set up, we need to again change path names here. So paths here, if I go to my paths, I need to have my pad stack path in, which as a side note, I deleted that $pad path and it wouldn't let me add it back in, so this is just the default directory. Sometimes if you're having problems getting to it, you can move up kind of what is considered the priority and where it looks for things. So basically it's saying it's going to first look in the pad stack directory, then it's going to look in the cadence directory for pad stacks. Now I need this PSM path as well. And this is the default PSM path, and then this one here was one that I am not going to be using currently because I believe all of my footprints that we are going to be using are on my D drive under cadence. Or maybe they're not. Maybe they are just D footprints. I'm going to go ahead and put that there, but I'm going to double check to make sure that's the directory I want. Yeah, that is the directory I want. That's got my footprints in it. These were the footprints that I had uploaded to the Blackboard site. And so I'm going to set, I'm actually going to move that up to being first. I'm going to click OK, apply, OK. Now we're ready to actually import the netlist. So I'm going to do import netlist. And we have to select what type of logic. There's HDL, which is another way to what some other circuit simulators would use, but we did CIS capture. Um, and then by default, since I saved it in the Allegro directory, it's going to look in that directory for the, and let me show you what I'm talking about. I selected the Allegro directory. I saved the board in the Allegro directory, so I'm going to go there. So my board file is going to be saved in here, or should be. Oh, it's probably not been saved yet. That's the reason. But you can see these are where those netlist files are. And so by saving in there, you automatically are in the right directory to import. But you can always change, and you can see right now it's in the Indiana Tech Cadence ECE 1000 Layout 1 Allegro. But you have to go to the directory where those net files were saved in order to properly import them. But because, again, I created the board file in that directory, that's automatically done for us. So I'm just going to hit import, and I'll see processing successfully completed. Great, so that means it imported everything. To finish this off here, we're going to go ahead and place all the components here. So I'm going to do place, and there's quick place. I like to do components manually. So and I'm going to select all the components, and you can kind of see there's a little footprint. And yeah, I definitely made my board too small. So we'll go ahead and place these components down, and we'll make a bigger board at the beginning of the next video. I don't know what I was thinking. And so I've placed all my components down. Now, this is what's called a rat's nest right now, because you have these blue wires which are showing the connections, but they're like kind of spaghettied, overlapping everything. And actually, the fact that I made my board too small is kind of fun and interesting, because you can look here and all these red little triangle like things that are pointing. That means there's an error in that you are failing one of your design rule checks. And I can show you how I can change one of them to not being a failure. See, that one disappeared because now this part is inside this package keep-in box. Now it comes back because it's outside it. So now, just as a general rule of thumb, I honestly don't always place all my components on the board to start with. I sometimes purposely place them off the board so that I can logically think about where they should go on the board. But we will get to that at the next video here as I recreate a larger board.